In this research paper titled, OptimAI, Optimization from Natural Language Using LLM-Powered AI Agents, the authors, including Raghav Thend, Yoran Sun, Ling Liang, and Haijiao Yang from the University of Maryland at College Park, present an innovative framework designed to make optimization problems more accessible. Optimization is a fundamental tool in science and engineering, used for tasks like decision-making, resource allocation, and even training machine learning models. However, the challenge lies in translating real-world problems, which are often described in everyday language, into precise mathematical formulations that can be solved by computers. This requires expert knowledge, which OptimAI aims to automate using large language models, or LLMs. The core idea behind OptimAI is to leverage AI agents powered by LLMs to handle the entire process from problem description to solution. The framework consists of 4 key roles that work together in a multi-agent system. First, there's the formulator, which takes a natural language description of an optimization problem and converts it into a clear mathematical formulation. For example, if someone describes a problem like minimizing delivery times for a logistics company, the formulator would turn that into equations and constraints that a computer can understand. Next, the planner steps in to create a high-level strategy for solving the problem. This involves outlining the steps needed before any actual computation begins, such as deciding on the best approach or algorithm to use. Then, the coder role generates the actual code to implement this plan, interacting with the computing environment to run simulations or calculations. Finally, the code critic evaluates the outcomes of the code's execution, reflects on any errors or inefficiencies, and suggests refinements for future attempts. This collaborative setup allows the agents to learn from mistakes and improve over time. The authors conducted ablation studies to test the importance of each role. They found that removing the planner led to a 5.8 times drop in productivity, meaning the system became much less efficient without a clear strategy. Similarly, eliminating the code critic resulted in a 3.1 times drop, highlighting how crucial self-reflection and error correction are. Additionally, they introduced a technique called UCB-Based debug scheduling, which is inspired by multi-armed bandit problems in decision theory. This method dynamically switches between different plans based on their performance, effectively prioritizing the most promising ones. As a result, it provided an extra 3.3 times gain in productivity, making the framework even more robust. One of the strengths of OptimAI is its emphasis on multi-agent collaboration. By combining different LLMs or AI models within the same system, the framework can explore synergies and handle complex tasks more effectively. This modular design allows for easy experimentation and integration of new models as they become available. In terms of performance, OptimAI was evaluated on 2 key datasets. On the NLP-4LP dataset, it achieved an impressive 88.1% accuracy, which represents a 58% reduction in error rates compared to the best previous methods. For the Optibench subset focused on nonlinear problems without tables, it reached 71.2% accuracy, cutting error rates by 50%. These results demonstrate that OptimAI not only outperforms existing approaches but also makes optimization more practical for non-experts. Looking at the broader context, the paper underscores how optimization underpins many modern technologies, especially in data-driven fields like machine learning. For instance, training a neural network involves minimizing a loss function over complex, high-dimensional spaces, while tasks like hyperparameter tuning or policy learning in reinforcement learning are essentially optimization problems. The challenge is that these problems are rarely presented in mathematical terms. Instead, they're described in natural language, such as minimizing delivery time or balancing investment risks. This is where LLMs come in, offering powerful tools for natural language processing and symbolic reasoning. They can bridge the gap between informal descriptions and formal models, making optimization accessible to a wider audience. The authors argue that automating this process could democratize these tools, allowing people without specialized expertise to tackle real-world problems more easily. Recent advances in LLMs have shown they can handle mathematical reasoning, coding tasks, and logical problem-solving, which makes them ideal for this application. OptimAI builds on these capabilities by creating a structured, agent-based system that mimics how human experts might collaborate on an optimization problem. For example, one agent formulates the problem, another plans the approach, and so on, with feedback loops to refine the process. The paper also touches on how different formulations of the same problem can lead to varying levels of efficiency. OptimAI addresses this by allowing the system to experiment with multiple options and select the best one, thanks to features like the UCB-Based scheduling. This adaptability is particularly valuable in applied settings, where problems might involve non-convex landscapes or high-dimensional data, as seen in machine learning applications. Overall, through OptimAI, the authors are pushing the boundaries of how AI can assist in scientific and engineering workflows. By reducing the barriers to entry, this framework has the potential to accelerate innovation in fields where optimization is key, from logistics and finance to healthcare and beyond. The results from their experiments suggest that with continued refinements, such systems could become standard tools for solving complex real-world challenges.